on a topic of renormalization of focal plane dynamics. There's a lot of famous diagrams that confuse some of the chemists in the committee. After that, he
were then dancing rings.
Yes. After that, he moved to Texas, where he was a postdoc working with Harry Sweeney. Now he's a group leader of something called self-organized complexity and self-assembled materials. And their statement of what they do is we perform interdisciplinary research on complex systems, among others nonlinear chemical reactions, electrochemical processes, complex fluids, self-assembly, condensed matter and biological network with emphasis on biological applications and new materials. We use experimental and theoretical methodologies from physical chemistry, statistical mechanics, and nonlinear science. Among his many contributions, perhaps not. The fact is that the three most quoted papers of Francesc are two papers in science, one on chiral sign induction by vortices during the formation of mesophases in steel solutions, another publication in Science on taming wind-free turbulence of scroll waves in excitable media. He also has a review of modern physics on spatial-temporal order out of noise. He has worked in a number of things connecting the stochastic processes, pattern formation. Then, as I said, no one is perfect, and he started to do experiments in electrode deposition and that type of thing. And we're going down to on his list of most quoted papers. I'm happy to see that number 13 is still a paper we co-authored on non-Markovian processes. And still going further down the list, I can find work that we did together, quite a few papers on liquid crystals. It seems it's not that much quoted, but I am.
You never know.
No, it's good. But I'm proud of the work we did together. And as I said, I'm very happy to have Francesc here.
Thank you very much, really. I really should also thank to Maxi to invite me, but actually I should thank twice because actually I in some sense I invite myself, so I don't think that's correct.
You have an open invitation.
Open, exactly. So no, it's really a pleasure to be here to meet Maxi and all the people. And well, now it has been so quite long since the last time I was here, but I hope that I will come soon now, that I can start that. And to tell you, to have the chance to talk with you and to tell something of our work and also your work and to learn a little bit from everybody. Anyway, I know that nobody is perfect. this I know. And I know that probably here to talk on experiments is a little bit risky. But I will talk about experiments, right? And in any case, I will also present theories and models. But I will try to convince you that doing experiments is something you can learn a lot from them. And actually, to be a little bit more precise, I will concentrate on a topic, well, not on a topic, I would say on a field, which is soft matter. Rather than to focus on a particular subject, a particular topic, I have preferred to just select different things, different topics, different scenarios, just to give you a sort of overview of the different things we are working. And I hope that this can be interesting for you and maybe not too boring. I will be pleased to answer your questions on these topics. Actually, I will be very, very brief on everything, so I will not give you the details on them, but I will be pleased to talk with you and to answer your questions, or either privately or whatever. I will be here if you know secret notes. I don't know anything, so I have time. Okay, now, the framework is soft matter, and I have tried to organize in two separate things. One is assemble monolayers, and the other stuff is paramagnetic colloids, and also I prepare some sort of subtopics. And I will try to follow. So, okay, first is assemble monolayers, and here I will discuss a very interesting finding on chiral symmetry breaking, which is something a little bit surprising at this level. Okay, first, just to probably you are not very familiar with Langmuir monolayers, so I give you a very brief introduction. Actually, it's on a slide. It's very simple. It's a system which is prepared just by preparing, let's say, a monomolecular thick, really ultra thin film of an amphiphilic compound. And this is prepared at the interface between water and air. So it's the simplest thing you can imagine. Actually, it's a very interesting system to do physics in 2 dimensions. Actually, it's the most perfect realization of a physical system in 2 dimensions. You control the Langmuir monolayer in terms of two thermodynamic quantities or variables. One is the temperature, and on the one is what is called the surface pressure, which is nothing but the reduction of the surface tension of this monolayer. And well, you can observe this monolayer, what happens there in different ways. The way I will be referring to here is using what is called Brewster angle microscopy, essentially a reflection microscopy. Essentially, this is shining light at the Brewster angle of water air. And this means that if the interface is just pure water, there is no reflection. And if something is going on there, if there is some compound there, then there is a pattern of reflectivity. So it's not difficult. These are examples of the kind of textures you see from this. It's a reflection pattern, actually. Okay, now I will concentrate on a particular system or a particular monolayer, which is prepared with an azobenzene compound. Don't be afraid, okay? Don't worry. Azobenzene is essentially a compound which has a very interesting property, and the property is that it can display 2 different isomer forms, two different conformations, and you can change between them by light. So it's photosensitive. It's essentially photosensitive. Now imagine you prepare your monolayer with a mixture of these cis and trans compounds. So you have your monolayer prepared with cis and trans. And what happens is that these 2 components are insoluble, so they cannot mix. And they prepare, or they organize themselves first as a sort of 2-dimensional emulsion. It's really a 2-dimensional like emulsion, consisting of droplets, these droplets, 2-dimension, which are essentially trans, and these droplets are embedded in a cis matrix. Okay? Now, this emulsion coarsens, so it evolves with time, and essentially what happens is that these domains, they fuse, and they form larger domains, and these larger domains, they also fuse, and finally you get a nice stripe-like texture like this, which is very similar to a smectic C texture in liquid crystals. Now, we were interested, well, first I have to say that the BAM image of this droplet is very nice, and actually it's very quantitative. It's not always the case. But in this case, the texture, let's say, the structure is very symmetric. It's very axial symmetric. So it's not difficult to reproduce the pattern of alignment of the molecules which comes from this texture. And actually you see here one of these pattern of alignment of the molecules. These red arrows, they correspond to the projection of the molecules. So you have to imagine that these molecules are not on the plane of the monolayer, they come out of the plane But here I show you the projection of these molecules, and you see that the structure they form is very, very similar. This is a particular structure which we call a splay, because the distortion in the orientation is like a splay-like. Okay, and it's very nice, it's very stable. Here I show you the BAM, well, not BAM actually, reproduced from BAM images of the different textures you can see. For example, here you can see bend-like structures. So the molecules here now they adopt a sort of bend configuration. And here, for example, you have a splays, again, as I show you. Either they can be in, with the molecules pointing towards the center of the domain, or rather out, pointing out from the center. Okay. What is interesting is that when the domains are small, they adopt this bend texture, this bend structure, and you can see here that there is a chirality, because you can have the molecules either going clockwise or counterclockwise. Okay, that's very important. Now, when you prepare a monolayer like this, since the molecules are not chiral, you have equal amounts of cis and trans. Sorry. You have equal amounts of clockwise and counterclockwise domains. So, I mean, there is nothing that breaks this symmetry. It would be very surprising to find an excess of either clockwise or counterclockwise domains. Okay.
Excuse me, but
Sure.
the domains are always of trans.
Exactly.
So the opposite...
The domains are trans domains, but organized either clockwise or counterclockwise.
But the cis, for example, never organize domains within a trans...
The cis phase, the cis phase with time slowly evolves into trans. It converts into trans, but it takes a very long time.
But it never, in the opposite way,
No.
saying that domains of cis of a trans C, it does not happen.
No, it doesn't. Okay? Now, interesting enough is that these domains, I mentioned this before, these domains fuse, they merge, and they form larger domains. And when you see that, you observe that they normally, they fuse, they merge when the chirality is contrary. So they fuse clockwise with counterclockwise. Okay? So at some point, by the way, and this process of droplet fusion is controlled by the dynamics of defects, and this is something I will not talk today, but it will be very interesting about what we have done on the dynamics of these effects. I will refer to dynamic of effects in another context a little bit later. But anyway, at some point we said, why don't we try to get one of these emulsions, but stable, not coarsening? And then, well, according to what I said, then it will be easy to achieve that if you control the chirality of the domain. So if you can prepare all the domains clockwise or counterclockwise, since they will not fuse, then you will get your emulsion stable. Okay? So we started to consider ways to prepare domains of the same chirality. And it turns out that the most silly proposal, most stupid in principle proposal, it works very well. And the silly proposal is just to use a steering. A steering with a magnetic stir, something you have seen in your chemical labs, in chemistry labs. This is small steering. You steer the subphase, the aqueous subphase, and this steering controls the chirality of the domains of the monolayer, which seems surprising. Seems surprising for many reasons, because you have a vortex or a vortex effect which is chiral. It's true, but it's centimeter scale, which is in the bulk of an aqueous phase, and this propagates down to a micron scale. This domain, I didn't say that, but these domains are typically 50 microns or 100 microns, it depends, but it goes down to this scale, and also goes from the 3D effect to pure 2D effect. This is something really funny.
But do you stir it before pouring on the surface or when it's already on the surface?
No, we stir before pouring onto the surface, and this is important actually. This is really important. Okay, this is what we see. So this is the stirring rate, and this is the sort of enantiometric excess. So the number of, in this case, clockwise excess of this domain with respect to the counterclockwise. And here you can see, maybe you cannot, but here you can see that the clockwise are this first quadrant is right, is very bright, and you can see that most of them, well, not all of them, it's not a complete resolution, but most of them are this way, and in this case, it's the other way around. Now the brighter sector is this one, and you see that most of them are here. And this is the excess. And this was really funny for us to discover. Now, the subtle explanation for that is the following. I will not go into details, but it's based on the process of obtaining these band domains. Actually, it turns out that these band domains appear because there are some precursors that are not circular, but that they are like ellipsoid domains. And when these domains fuse, and I have a video here, we will see it, when these domains fuse, they fuse, here are two ellipsoidal domains, they fuse through the appearance of two defects, two minus 1/2 defects, and these minus 1/2 defect recombine, and finally you go from, there is a shrinking line here, this line finally collapse, and you get finally the sort of membrane texture. So it's a question of really a defect dynamics, the defect dynamic problem which controls the fusion of these ellipsoids, giving rise to this band. And what happens is that when you have your vortex stirring the upper phase, then it's a question of the chirality introduced by the vortex is associated with the chirality of pairs of these ellipsoidal domains. Here you can see, it's a cartoon, here it's a singular defect, which is a plus 1/2 defect at the end of one of these ellipsoids. This is another defect, which is a sort of escape defect. It's a defect which is not really inside the ellipsoid, but it's outside. When these two guys meet, and when they merge to the appearance of two 1/2 defects, two minus 1/2 defects. And now it's a question that these two recently appeared defects recombine with the existing real defects here, and finally you get that. Now when it is the other group, this is the configuration that gives rise to a clockwise domain, which is essentially the sign of the vortex here. When the configuration of these two pairs are the other way around, so it's counterclockwise, then you have that the encounter of these two ellipsoids is going to happen through two 1/2 domains which have closer the escape defects here, rather than here that they have closer the real defects. So in that case, we interpret that this annihilation of defects is not favored, and so it's a kind of non-active encounter. So this encounter doesn't lead up to sort of thing. So these encounters are favored, these encounters are not favored. So this is essentially the idea behind this thing. Again, if you are interested, if you have not many more details, but let me go to the second scenario. Okay, so far so good. So we were able to, in some sense, control, to select the chirality of these domains, and then you can say, well, this is really useful for something. And it's true that if you always work at the interface between air and water, this is not very useful. I mean, if you imagine, for example, of using these domains to, I don't know, something for optics or whatever, you always need to transport this monolayer to a solid support. So we said, okay, let's try to transfer this monolayer into a solid support, right? And the first question was, well, how do we do that? And the solution is really standard in physical chemistry. It's a technique which is called Langmuir film, and consists simply in taking a substrate and then putting the substrate here through the interface and then putting that. So, and then the monolayer gets stacked into the substrate. Now, first question was, oh, by the way, here it's a slide just to show you that at some point you want to prepare. Okay, let me skip this. Doesn't matter. Let me skip. I come back. Now, the first point was, is this transfer process really good? I mean, is it possible really to have the same domains, these droplets that we had at the interface water? Is it possible to have them at now that you have transferred the monolayer? And the question was, well, how do we observe that now? Because we cannot use the Brewster microscopy. Brewster microscopy can be used when it's in the interface in the word manner, but not in this case when it is transferred to a solid report. And then we imagine a very simple way to really image these domains when they are transferred at this substrate. And the idea is to put liquid crystal, a liquid crystal on top of this. Okay? Now, if the transfer process has been successful, then in principle we should observe, just by polarizing microscopy, a usual way to observe structures in liquid crystal, you should observe these structures at the cell. And this cell is prepared. Look, this is the transfer monolayer here, and this is another complementary plate which can be prepared, for example, with some sort of anchoring. That was the subject of the slide before. I mean, you can prepare this anchoring here, either planar or either homeotropic. Doesn't matter. Okay, these are the images you see when this anchoring here is planar. Okay, so you take one of the substrates which contain the monolayer transfer, and the other one is a substrate, which is a microscale, doesn't matter, but it's prepared with a liquid crystal with a planar anchoring. And this is what you see. So essentially you see that the transference has been successful. And you have the domains you had before, you also have that here. But then the question is, okay, this chirality we have seen before, is here also present? And how is it manifested? And it turns back that really this chirality is transferred also, obviously, and you can see, for example, two different kinds of domains here. One has this wall here to the north. I hope you can see. This one goes to the south. This sort of wall. It's a kind of discrimination line. I will be a little bit more precise here. I have to say that we fill the cell from this side in the pneumatic. We fill a cell with the pneumatic. And also this is the rubbing direction to prepare this planar alignment of the liquid crystal. And as I said, there are the two kinds of domains, the CB and the CCB, the clockwise, counterclockwise. They display a wall in the north part here or in the south. And by the way, here you can see a mixture, and we were able to capture really the process of merging of one clockwise and another one counterclockwise, and you can see the wall here and the wall here, one to the north, one to the south, because it was really captured at that moment from the monolayer. Okay, it was nice, but the structure itself, it's interesting. I mean, this kind of discrimination, what is this? I mean, this is very strange. I mean, what's the structure of this? We did before something else. This is again one of the images, this discrimination line, this wall here, this wall here. We did something else. After filling with the pneumatic, we just heated. So we went to the isotropic phase of the pneumatic material, and then we cooled down. And then this wall disappears. And two discrimination line now appears, but very different from above. Because here, this direction is, remember, perpendicular to the far field direction, for example, to the direction of filling. Here, these lines are oriented parallel to the, for example, the rubbing direction, the direction in which the support was rubbed to prepare the planar alignment. So, okay, so we said, well, this is a little bit funny, so we decided to do fluorescence confocal polarized microscopy to see better the structure, the 3D structure of these structures, of these defects. And it turns out, well, here are the two different polarization configuration, and here it's a sort of cartoon of the structure of the liquid crystal when it is in contact with the monolayer. The monolayer, the transfer monolayer, should be here. And imagine what happens in the region where the molecules at the monolayer are pointing like this, but you are filling your pneumatic like this. So there will be a problem there, there will be a conflict. Okay? You can imagine that there will be something problematic here because some molecules from the support are pointing this way, those arrive this way, so that's a conflict. So what happens is that these molecules, they turn from this monolayer substrate, they turn for half pi at some distance, some penetration distance from the support, and then they turn half to more up to having the direction of the flow. So you really have your molecules like this, so they enter like this. So these molecules first they turn half turn and then they get back to complete the full pi turn to have the same direction as the flowing direction. Here I show you another representation of this wall. It is from a technical point of view. The discrimination is an integral strength discrimination which connects a singularity of charge, topological charge +1 at the center of the domain, with a topological defect -1 which appears at the contour. I will just skip a little bit this, but anyway, just to say that we also have performed the same imaging for the case where we have transited the isotropic phase, and in this case, the discriminations are a little bit different. In this case, the molecules are like this in the two hemispheres, and in between, in the equatorial plane, there is these two arcs of half integer power. By the way, probably you have noticed, but these are really the representation in a vertical section of the cell. So this is really, you see here the penetration of these defects from the monolayer, from the transfer monolayer to the liquid crystal cell, which is very, I think for me it's interesting to see how they propagate. Actually it's also interesting to see how this penetration length depends on the thickness of the cell of the liquid crystal, and you can see more or less that they scale. I mean, the penetration is always small, but it scales more or less with the cell thickness up to some very small cell thickness where it is really very, very thin. Actually, you could ask me whether one of the two modes, I mean, one of the two structures, either the single discrimination integral of the two arcs with semi-integral discrimination, which one will be, from an energetic point of view, favorable? Well, we have done some estimations of the two energies, of the two free energies of these defects, of this discrimination line, and it turns out that they are very, very similar. So it's the preference of one or another. It's not a question of energetics, it's a question of the preparation really of the material, of the way the cell is prepared. And in one case it's just filled with the pneumatic, in another it's prepared with that, flow with the pneumatic, and then transited temperature cycling to isotropic and then back to the so that seems to depend, that makes the difference. And actually this was also confirmed by some experiments with impulse optical. Okay, this is the first part. Okay, it's the part of Langmuir. Then I continue with the second subject. So if somebody who's not interested in Langmuir now maybe has the chance to become a little bit more interested in colloids. Here we'll start with colloids. We have done a lot of work on colloids. Essentially, our system consists normally in colloids, small bits, which are paramagnetic. So they don't have a permanent magnetic moment, but they are paramagnetic, I mean magnetized by an external magnetic field. And normally, but not always, we use these dispersions of these particles disperse or pour on top of a structured magnetic field. Not always. So the first things I will talk you will be this way, but other examples not. This structured film you can prepare different ways, but most of the time we use prepare in stripes of opposite magnetization, up, down, up, down. Okay, now the first scenario I will tell you is a scenario where when you apply a magnetic field which is oscillating in a plane which is perpendicular to the plane of the film, then you obtain a sort of ratchet or directed motion of these colloids. Okay? It's reversible, so it's very, very well controlled. Actually, this is the way to prepare this or to obtain this ratchet motion. You force the system with a magnetic field which is oscillating, as I said, in this plane with some angle, theta. And the principle, I mean the explanation behind that is essentially the fact that this component of external magnetic field, this vertical component, makes these stripes to expand if the sign of the magnetization is equal to the direction of the field, or they shrink if the direction of the magnetization here is contrary to this vertical component. Now, this X component, what makes is breaks the symmetry in that direction and makes some of these block walls stronger than the other one. So this strong wall here, this block wall here between these domains, this block wall is higher when the component X is positive, and this is smaller. So the particles get pinned here in this block wall. Now, when they change, when the phases change, then it's the other way around. This block wall is now pinned, is now stronger, so it pins the particle stronger, and this one is weaker. So in this way, you really achieve the ratcheting motion of these particles, just hopping from block wall to block wall. Okay, that's nice, very nice. You can obtain ratcheting, but then at some point
How do they call it? So it's thermal diffusion or what?
No. It's really magnetic forcing.
Okay.
No. That's the point. I mean, what is the role of the thermal noise here? Okay. You will in this video there is no magnetic field applied. So the particles are more or less pinned to these block walls, and then you say it's very hard to see here any kind of motion. I mean, actually there is some motion. There are some particles, if you look very, very in detail, you will see that they move a little bit. But essentially, thermal noise under these conditions is very small, because the particles really are pinned to these block walls. Now, what happens when you apply this forcing magnetic field, and then you have this ratchet move, and what happens is this. This is the ratchet in this direction, but in the transversal direction, there is a lot of wandering around. And actually, performing different experiments, you can see that this transversal motion is actually diffusive-like. So it's Brownian-like, I mean. But, and this is a big but, with a diffusion coefficient which compared to the diffusion coefficient without the magnetic field might be up to 3 orders of magnitude larger. So that it's a real giant transversal diffusion which you have when you are forcing this ratchet mode of these colloids.
But the fluctuation does not play a role in the movement along the direction. or in the transverse direction?
The fluctuations are in the transverse direction. Actually, you can see here the trajectories.
So the fluctuation does not play a role in the movement on that direction, which is the typical what happens with the ratchet, that the fluctuation is, so here this is all the
transversal.
Yeah.
It's transversal.
Just transverse. So
it's just transversal. It's not the normal enhancement of diffusion in the same direction that you have the ratchet, but it's just of the opposite, on the orthogonal direction. Now, we prepare a model for that, and the model is extremely simple. It's stupid simple. First, just an indication of the basic mechanism of the ratcheting. The basic mechanism of the ratcheting is hopping between in a potential. This potential is the potential corresponding to a particular phase of the cycle, and then in another phase it goes like this. So the wall now the deep disappear, and then it goes back, and then in this way the particle is just a sort of ratcheting. Okay, back. You distinguish here in this motion, you distinguish two times. First, the time of hopping. And this time of hopping or jumping, it turns out that it is independent of the frequency in which you are. I mean, the frequency is important because the frequency controls the motion, the velocity of the ratcheting, the frequency which you are forcing. Now, it turns out that this jump time is independent of the frequency. So, another time is the exploration time. So the idea is that the particle spends its time first just exploring when it is in this volley, and then it has to jump. Now, this prescription turns out to be quite reliable. I mean, these are real experimental measures of this exploration time, how it depends on the frequency, and from that, then the idea we have is the following: we will prepare a model based on the following. There is an element here which I didn't mention up to now. These stripes, these block balls, are not perfect. They are subject to inhomogeneities. And these inhomogeneities, you could imagine that they introduce some sort of random potential, random magnetic potential on the transversal direction, right? Then, the very simple model is the following. We will prepare a model based on a relaxation dynamics along the transversal direction, just without noise, nothing, without thermal noise, and just assuming that this potential is random, the random magnetic potential. Now, the jumps between the block walls are, in a sense, a way to reset this random potential. Because when you jump, you enter into another realization of the disorder. Okay? So, what we say is, okay, suppose the simplest thing, suppose that this potential, transversal potential, is made of parabolic pieces. All of them with identical curvatures, but with some random extension around their minimum. And each time the particle jumps, it goes to another position in this landscape. If you do that, it's quite easy. The equation of motion is trivial. It's this linear equation. You can integrate. You integrate it in terms of here this quantity, which is essentially the displacement at each time, the displacement with respect to the closest minimum of the volley. And then after p half periods, you sum up this, you accumulate this displacement, and you get this. And this, you can assume that it's a kind of independent, identically distributed random numbers of zero average and some sort of variance. Now,
excuse me, the tau E, the exploration time, is an input or an output?
Tau E is an input.
It's a parameter.
It's a parameter. But it's a parameter that depends on the conditions of your experiment. It's controlled by the frequency, essentially. Okay? With the frequency diffusion. Okay, so you finally end up with this expression for the diffusion coefficient in transversal direction, and you fit with two parameters. Essentially, one is the distortion of this noise, this sigma, and the other one is this sort of recovery constant, this spring constant. Essentially, this dispersion has to do with the length scale of these block walls in homogeneities and is of the same order of the size of these particles. By the way, we mentioned these particles are typically 1-2 microns, typically. And this spring constant, well, is some sort of inverse of the characteristic time of relaxation. And the fit is really, really amazing. It goes really very, very nicely. Now, another step. Now, what we are studying is collective effects on this chain, and it turns out it's a very interesting scenario also. When you see not an individual particle ratcheting, but a sort of chain ratcheting, you will see that there is a sort of collective behavior here. And actually, we have analyzed this collective behavior, for example, in terms of the mean square displacement of the end-to-end distance, and we have seen that this behavior goes from diffusive to subdiffusive. But what is it's really funny, is that we have been able to demonstrate that it's very similar, this behavior, to the behavior predicted by the Rawls-like model. Rawls' model or Rawls' description is very familiar in polymers. No? It's really a typical description of a polymer chain. The Rawls model is based on springs and beads. And it turns out that some of the predictions of this Rawls model seems to apply to this case. Okay, this I don't have time. If somebody interested, I'll give you some details. I only mentioned here some other possibilities for using these garnets, localized ballistic. You can have other kind of transport modes, localized ballistic, diffusive. You can transport cables. You can sort in particles by size. You can do everything. If somebody is interested, we have already here to publish very easily. Now, the second thing is to try to transport these colloids, but not using a structured magnetic field, but just using a simple glass support. And it turns out that you can do that in terms of preparing these colloids as swimmers, micro-actuated swimmers. I skip this because this is just to say that when you are in the low Reynolds number regime, equations are time reversible, so in principle, swimming modes based on a single degree of freedom, they are not possible. And now I go to the realization, and then I go to what is the model. The realization of these swimmers is to take two of these particles, two of these colloids, and to link them. And you prepare a doublet, a non-symmetric doublet. One particle is bigger, the other one is smaller. And you link them using DNA. It's really simple. It's very complicated, but it's really very simple. You use a 25 base pairs, a chain, and you link them. And this link is very stiff.
What do you mean by linking?
Linking, you prepare one of these beads is functionalized with what we call streptavidin. The other one is essentially the same, streptavidin. And then you have a DNA chain, which is at the end they have biotin, and the streptavidin and the biotin they link. So you have one particle with a DNA chain, and then the other one has the complementary bases. So the two chains link, and then you have the two particles tight. It's very stiff. It's hard to separate them. To separate them. It's really, there are some details here. There are some details. If somebody is interested, there are some problems here. And if you think a little bit, you will see probably that here there will be some problems. And if somebody has that, I will tell you. Anyway, when you have the doublet, now, without anything, no magnetic field, nothing, no magnetic field, no structure field, you just subject it, you just force it with a processing magnetic field. It's really very, very simple, okay? And what you see is this. you see, you realize a swimmer. You observe from the top. Huh? And you see here one of these doublets propagating. This one, by the way, is a single particle and doesn't propagate. So this means, by the way, that there is not a question of the magnetic field which is not homogeneous, which is not uniform. No, it's nothing to do with that. It's really another thing. Okay, we have characterized the velocities in terms of essentially two control parameters. One is the frequency of precession, and the other one is the angle of precession of the magnetic field. And you see here in some behaviors of this velocity, some maxima, some here and here. Well, it's nice. I mean, it's not a big velocity. It's not a big velocity. It's 3 microns per second, but these particles are very small, so you have to compare. I mean, it's 3 microns per second for an object of 2-3 microns is not that. Now, what is the origin of that? And that was for us kind of mystery for some time, and then finally I think we got some answer. In this video, I show you something. I show you again, looking from above, the doublet, and you will see that the big particle doesn't go out of focus, but the other one, it goes periodically in and out of focus. So essentially, this means that actually the cartoon you can prepare of this motion is as follows. You have the big particle, you have the small particle. Now this big particle practically doesn't move. I mean, doesn't move vertically, sorry. It moves horizontally, but doesn't move vertically. This one is rotating more or less around the big one. Now, in doing this, you will see that in this phase, for example, you can think that the object, the doublet, experiences a higher drag, a higher viscous resistance actually, because this part goes closer to the support. So in some sense, then what you do is a kind of, you rectify your perfect reversible motion in terms of a directed motion, because there is a sort of asymmetric dissipation. There is a high dissipation in this phase with respect to that one. So in some sense, it's an object with a single degree of freedom, but the fact that it is very close to a boundary actually makes it, as it would be, not a single degree of freedom object. Yeah.
So it's a magnetic torque that is making rotation.
It's a magnetic torque.
And
okay?
This interface between the phase and so these lines.
This is water. This is water. I mean, it's nothing else. I mean, it's close to the substrate. It doesn't touch substrate, but it's very, very close.
Okay, so it's not immersed in water, but just
No, it's immersed in water.
Uh-huh.
It's immersed in water. I mean, this is water. But it's very close. It goes very close to the surface, to the confinement surface. It's glass plate.
So somehow you're rotating on top of the double layer of the, and that's what makes it.
Yeah, but it's not a problem of the double layer. It's a problem of this motion, as it's in the model I will show you. It's a problem of the coupling of this motion close to this boundary.
So,
It's not
these lines you will have plot here, these dotted lines. What
This is nothing. This is just to show you, in some sense, the water here with the boundary layer which is created here. It's more pictorically. I mean, it's.
So the thing is just walking, right?
It's like a bicycle, not without direct contact. Yeah, exactly. If we were correct, then a very simple proof is to show that if you only apply half of the cycle, you don't make this guy move, and it is true because you need both phases. You have to have really a symmetry in the two phases, and you can see here that they don't move, and this is the model. I will skip more of the details, but anyway, there is an hydrodynamic part, there is a magnetic part. Now, the hydrodynamic part consists in using the Austin-Intense formulation based on the mobility matrix and the forces applied here. This is the doublet, this is the director connecting the doublet, and by the way, this director is coincides with the direction of magnetization when you apply external magnetic field. Now, it turns out that you make some reduction or some hypothesis regarding the mobility matrix. Now the nice thing is you can connect the velocity of the center of mass and the rate of precession of this director. And both quantities are related directly in terms of some matrices, was essentially they come from these mobility metrics. Now, with making, as I said, some assumptions, you finally get out an equation for the velocity of the center of mass in terms, as I said, of this rate of precession of the director. We assume, by the way, that there is synchronization. I mean, this director rotates with the same frequency that the Paramagnetic field, which happens at these frequencies. And when you do that, then you couple this part, which is the hydrodynamic part, with the magnetic part. Now, the magnetic part is just you write the torque, and the torque is the magnetization, essentially the magnetic moment times the external magnetic field. You prescribe a kinematic equation based on, You prescribe a kinematic equation based on in terms of this angular velocity. This is a rotational viscosity or rotational coefficient, and then you plug it here. You prescribe a solution, which is a solution for this director, and you end up with an equation here for the velocity in that direction, which is analytic. It's completely analytic. And this is the comparison with experiments, which compare really well. There are only two parameters here to fit, and two parameters that we could not obtain all the way around. One is the distance of the center of mass from the boundary, from the support, from the glass support, and this comes to be, or turns to be 2 microns. This is very reasonable, but this from experiments you cannot really get it. And the other one is the rotational viscosity, which for us it was not difficult it was really difficult to estimate, and so that was the parameter of fitting parameter. Actually, it's reasonable, apparently this value, but with these two fitting parameters, you obtain a very nice accuracy between the theory and the experiments. I just want to mention that from here you can imagine doing a lot of things. For example, you can really direct the motion of one of these doublets, and then you can, for example, this is a microfluidic channel, and then you can imagine here some properties of directing cargos or transporting things. By the way, we got a patent from that, but nobody buy it. So I don't have to continue doing research. And the last thing, I come back to the first scenario, and I come back to Maxi. Maxi said at the beginning that we started doing research on the crystal of Frederick condition. Now here you will see again the Frederick condition after 25 years. What we did was the following. With these nice beads, colloids, we stretch them. If somebody's interested, I tell you the way we do that. We stretch and we prepare ellipsoids. And when we have these ellipsoids, what we do is the following. We put these ellipsoids inside the liquid crystal matrix. Okay? Now, this is the liquid crystal matrix with homeotropic alignment. Here, molecules like this, here, molecules pointing like this. And we apply an electric field which is perpendicular to these plates. Now, if this material has a negative dielectric anisotropy, what happens is these molecules will turn this way and will stay planar, okay, parallel to the support. But what happens here is that this configuration is highly degenerated. So you can imagine, you have rods like this. If they come to go that way, they can adopt any configuration, any azimuthal degeneration that way. So at some point, we wanted to try to control this degeneration using ellipsoids immersed here. So here, no ellipsoids, just the transition, the electrical Frederick transition, so the molecules going planar. We put a magnetic field, nothing. Well, that nothing happened. By the way, these are images from microscopy. Now here we put the ellipsoids. Actually, to be precise, here we use conglomerates of the spherical particles. They more or less align with the pneumatic liquid crystal. Then we apply the electric field. They again follow the liquid crystal matrix. But then here we apply a magnetic field and we orient these ellipsoids or these conglomerates. What happens is that then the liquid crystal matrix rearranges, orients, follows these clusters in the area around them. Because then you can really orient your inclusions, your magnetic inclusions, and you can break the degeneracy in the plane of the liquid crystal. And actually it's even better, because then you can start, for example, to rotate in this case it's real ellipsoid. You can really rotate in plane the ellipsoids, and what you do is you accumulate torsion in the liquid crystal material, and this accumulation of torsion results in a target pattern, which is something really very, very amazing. Actually, this structure was predicted by this end. It's called magic spiral. It was predicted by this end in 81 or even before that maybe, and we have realized it. And actually, by the way, for example, it's completely reversible. No, it's funny. I mean, you can really torque the liquid crystal with the magnetic inclusion, and then you relax, and the liquid crystal goes down. It's funny. Actually, we can even do more, because we can prepare helix-like structures. If you apply an electric field which is not the complete, I mean, very well above the Felix position, so if the structure is not really going really very much to planar, but is somehow between the planar and the neutropy, then the structure turns out to be three-dimensional, not pure two-dimensional targets, but three-dimensional. And here I show you some of these structures. And it's funny because then in these structures you can see the chirality of the rotation of the magnetic field. So in the previous structure, the target, you cannot realize what direction you have rotated the magnetic field, but here you can see different helical structures depending on the rotation direction. Here, I don't know if this is clockwise and this is counterclockwise, rotating the magnetic field, but you can see that they are different. Okay, with this I finish. I'm sorry, I'm being a little bit late. This is the work of many people, as you can imagine. Actually, I can only here explain what other people do. Also, I do something that is most of the work of these people, Paret and Petit, on the experiments on assembled monolayers in Barcelona. The experiments on polarized confocal microscopy were done in Boulder, Colorado, with Trevedian's man group. The work on the paramagnetic colloids is with essentially the work of Pietro Tierno and on the PhD Sergio Hernandez. The theory of micromotors is done with Ignacio Pagana Barraga and Rami Dorestani in the University of Sheffield, and the giant diffusion was also a contribution by Peter Weinman from Bielefeld. And last but not least, I have talked of many things, but I could have talked of many other things. And here I show you some of the different topics I'm working on in the group, non-chemical systems, from propagation reactions, diffusion question, chemical soft matter. Apart from the soft matter I mentioned, there are also aspects of microfluidics which are very, very interesting. Also, I'm doing something on craft formation in grains, essentially models of craft formation, models in developmental biology. I mentioned this moving to Raul. I have done quite a lot on this. This is done with Ramon Reigada. This is done with Javier Luceta, essentially the problem of boundary formation and how this boundary formation, for example, the larva of the Drosophila, keeps stable under proliferation of cells. And finally, with Maria Angels, the last thing, metabolic networks. We are very, very interested in E. coli metabolic networks, and we want to cartograph or zero refine, so using all what Maria Angels knows, that is a lot, but applying it to metabolic networks. And thank to you very much.
Thanks for the magic mystery tour on soft matters.
It's a mess. Yeah. So,
More questions, comments, criticisms?
go ahead. I mean, please feel free. I mean,
The experiments are always in the room temperature, or
Yes.
just
well, essentially all of them. Yeah, it's essentially at room temperature. Yeah, essentially. In the Langmuir monolayer stuff, sometimes the configuration change quite a lot on depending on the temperature, but normally we're working around normal temperature. Yeah, I mean,
I'm still lost with this in the first part when you prepare the domains with a given chirality, and
Yes.
you say that you join ellipsoids, but I don't know where you join them by where do you steer. You say you steer outside of the surface, but I don't understand this.
okay.
So where do you do that? You say before pouring the
Okay, wait. You have a petri dish. Okay? You put a magnetic sphere. You steer. And when you have this, then you take your amplifier compound and you drop there.
okay. So you are not steering the amplifier. You are steer the water.
Steering the water surface. Yeah. You steer the water, but we steer the water surface, but you know the water surface is running also.
Okay. No, but you are steering. So the steering is on when you pour the
Exactly.
Okay.
Exactly.
But when you still at 9,000 revolution per minute.
Yeah, and you
That's
say,
not
how is
really
it
vortices
possible?
or anything, or?
The vortex is quite big. It's true. And one of my surprises is that the monolayer will think, oh my god, this monolayer will get completely amazed. Well, actually, I have to tell you, I mean, this, for example, the video I show you, this video is not obtained when steering. Because when steering, you cannot see anything at all. I mean, with the band, you cannot see anything. This video is obtained at rest. But the thing is, when you finish the steer, and the monolayer is there, and you see that this fluorescence process has taken place, and so the monolayer, I cannot tell you whether the monolayer during the stirring keeps completely intact, keeps completely as a sort of completely non-separated material. This I cannot tell you because we cannot really observe directly the monolayer. But it's true that either it stays there during the stirring, or if not, you observe what happens after stirring, and in principle you have seen all the dynamics that in principle is induced by the stirring, and you see the state of the monolayer after stirring. It's not destroyed. It's not destroyed. After that, so yeah, please.
Do you understand what mechanism limits the excess of one chirality due to the stirring?
No.
Because it was about 50-60%, or?
No, we don't understand. Yeah, it was something like it's 40. It's an assessment numeric of 40%. This means this essentially is the difference between the number of one side and the number of other. So probably is 80, 20, no 70. 73, that would be 48. No, we don't know that. We don't know that. Actually, now we are doing something which is also very interesting, and is we add a tidal doping, a chemical tidal doping, because then what we want is to see whether this effect, this sort of physical effect can be counterbalanced by this chemical effect of tidal reduction, or not, or the other way around. So, but specifically what you asked me about this limit, I don't know. If this 40 or could be I don't know. I mean, complete resolution, this will be very difficult to obtain, because if you remember the mechanism, actually is a sort of different kinetics. So if it is true, I mean, and it's based on different kinetics, it's hard to imagine that will be perfectly 100% resolution. So this mechanism will be perfect to that one, but not to a 100% probably different, you know. So it's not completely unlike that you're going to obtain its complete resolution, but the amount exactly why 40 or I don't know, I cannot tell you.
I have one myself. I mean, the swimmer. Swimmer makes a good sexy name for a title, but is it really swimming or is it pushed by the magnetic field?
It's walking.
No, actually,
Walking with a single foot.
exactly.
Yeah, but I mean,
water is swimming.
No. It's true, Maxim. It's true that the use of swimming is an abuse of language.
No.
Because it's not autonomous.
yeah, but that was my real question. Have you thought of some type of, all these games that you play to have really something which is self-propelled?
Yes.
And?
That is another talk. Yes, very easy, Maxi. When you have these ellipsoids, okay, maybe you cannot see it very well, but anyway, when you have these ellipsoids, you cover them with platinum. One of the sides you cover with platinum, and then you put in hydrogen peroxide, oxygenada, H2O2.
Okay.
Now there is a reaction between the platinum and the hydrogen peroxide, and this guy propels autonomously. It's like a rocket. And it's even better, because then, since the particle is ellipsoidal, and you can really direct the motion of this rocket. Because with a spherical particle, you could do the same, but then it will go. But if it is ellipsoidal, then you can drive it with your magnetic field. And this is another paper. This is
but I don't want it to be driven. So you really have some chemical or physical modes of self-propelling particles.
This is self-propelling particle.
Now, and if you put many of them,
crowd motion, float motion, floats. I don't know. This is something, I mentioned this morning. For example, with the swimmers, we wanted to study collection of these guys. Collection of
those you are pushing them.
Okay. The ones that they are autonomous, we don't know. But this will be a very interesting question. To study collections of assemblies of these guys, whether they synchronize, whether they organize in flocks, or there is some leader going there, or I don't know. This we haven't done. But to obtain autonomous motion, this we have done with this strategy. So we have prepared many different toys to play with.
Okay, more questions or comments? So your last thing, it is clear that Maria Angeles has to come another time to give a talk.
Sure, now she should explain you our cartography.
Okay, Francesc will be here during the afternoon.
Yes,
if anyone
and I will
is
be
interested in talking. Thank you.